So.
Sarah's got questions.
Good.
Yes.
What will we do with that, Sarah?
I got questions too.
Okay.
I'm really having a hard time wrapping my mind around spanning. So maybe we could talk about that.
Okay. Should I give general comments and then we'll dig into a question?
That sounds good.
Okay. So, V will be a vector space over some field F. And we'll say that S spans V, or is a spanning set. If every element of V can be written as a linear combination of elements of S. In other words, in some sense, I mean, to make an analogy, I don't know if it's a good analogy or a bad analogy, you can kind of think of the primes as the building blocks of the integers, in that you can get every positive integer by multiplying primes. You can think of a spanning set as sort of building blocks for a vector space, because you can get every element of the vector space by taking linear combinations of elements in the spanning set. So just as you can get every positive integer bigger than 1 as a multiple of primes, you can get every element of the vector space as a linear combination of elements in the spanning set. Remember, factorization into primes is also unique, so not only are the primes the building blocks of the integers, but you build things up uniquely, like there's only one way to write 160 as a factor of primes. When you become a basis, that means not only can you write everything as a linear combination of things in the set, but the representation is unique, because the linear independence makes the representation unique. All of that will come out in the wash. Should I write down more general comments, or do you want to toss out a question? Because then I can talk about, if you know the dimension of the vector space, sometimes you get information about spanning and linear independence free of charge. Should I write that down?
It doesn't matter to me how.
Okay. So, suppose.
Is this section in chapter 14? No.
Yes. This is terrible. Sure.
Well, 14.3, I wrote down
three.
determining spanning set and linear independence. So I'm assuming this is the section.
Yeah.
Okay.
I mean, it's been a while since I wrote this. I do remember that I told you that I signed my contract the day after the 2012 election, because then I figured I could tell everyone the joke, yeah, I'll sign the book contract the day after we elect a black president. So I thought that would be a nice, appropriate thing. See, amusing to you back then. Okay, so suppose the dimension of V is n. And 1, if the number of elements in S is less than n, then n cannot be a spanning set. So if you're in a 5-dimensional space, and if S only had 4 things in it, it couldn't be a spanning set. If the number of things in S is more than n, then S cannot be linearly independent. And 3, if the size of S is exactly the dimension, then S spans if and only if S is linearly independent. So if you're in a vector space and you know what the dimension of the vector space is, if you're trying to determine whether things are, so suppose you're in a 12-dimensional vector space, and I give you some set. And I said, okay, is this set spanning? Is it linearly independent? Is it both? Is it neither? So there are two things you have to figure out: spanning and linearly independent. Two questions. Well, it turns out, if you know the dimension of the vector space, you only have to answer one question. Because if the set is too small, then the answer to spanning is no, and you only have to worry about whether it's linearly independent. If the set is too big, then the answer to linearly independent is no, and the only thing you have to worry about is whether it spans or not. If the set has the exact size of the dimension, in other words, if the number of elements in the set is the same as the dimension, then there are technically two questions to answer, the spanning question and the linearly independent question, but the answers to those two questions are going to be the same. So hopefully, one of those is easy. So in each case, if you're wondering whether or not something spans or whether or not something is linearly independent, it looks like there are two things that you have to determine, but because of what's written there in the lower left-hand corner, you really only have to answer one thing, because the other one you get for free. Okay, so there's the background. Now, you probably want to look at something specific. We must have some exercises that would bother you.
Yeah, I mean, I think the beginning of 14.3.
Okay, 14.3.
Like number 11
Okay, so number 11.
and number 9 are the ones that I have questions.
Okay, so in problems 1 through 12, we are looking inside of R4.
Number 11?
So we're working inside a four-dimensional vector space. So we immediately know any set with more than 4 elements can't be independent. Any set with less than 4 elements can't span. And if you have 4 elements, you span if and only if you're independent. So, in number 9, do you want to read off the 4 tuples?
3, 0, 1, 1, 1, 0, 2, 2, negative 1, 0, 1, negative 1,
Negative 1, 0,
1,
1,
negative 1,
negative 1,
2, 0, 3, 4, and 4, 0, 1, 1.
Okay, so inside this four-dimensional vector space, we've got 5 elements. So if the set has 5 elements, the number of elements is more than the dimension, so it can't be linearly independent. So the linear independent question we get for free. The spanning question, we have to do some work. Now, one thing that we had is, if there was a simple spanning set, so let's call this set S. If you could find an easy spanning set let's say T, such that T is contained in the span of S, S spans. So, in other words, for S to be a span, and I'll say why this is a useful observation. To be a spanning set, you have to show every element of V is a linear combination of the elements of S. That's every element of V. But how many elements does V have? V has an infinite number of elements. That means technically you'd say, well, there are an infinite number of things I have to check if in a span of S. It takes a long time to check an infinite number of things, right? But it turns out, well, you don't have to check every single element of V. It's enough to show that some nice spanning set is in the span of S. So, in R4, what's the easiest spanning set you can think of? So that's probably the easiest spanning set you can think of, right?
Yes.
Now, again, technically speaking, to show that you're a spanning set, you need that every element of the vector space is a linear combination of the things in S. But it turns out you only have to show that these four things are each linear combinations of things in S. So, I have to show that each of these four things can be written as a linear combination of these things. Well, it's going to take a little bit of work, but if I sort of play with these things, what you might notice is these things kind of look like these things, right? Like 0, 1, 1, and 0, 2, 2. So let's give these things some names. V1, V2, V3, V4, V5. If I took V2, 1, 0, 2, 2, and took away 2 copies of V1, what that's going to equal is, so I take this minus 2 copies of this, and that seems to be -5, 0, 0, 0. So -5, 0, 0, 0 is in the span of S, right? But if it is, so is when you multiply this by -1/5, that's -1/5 of this. That's 1, 0, 0, 0. So that one's in the span. So everyone agree that 1, 0, 0, 0 is in the span of S? Now, what this means is, when I'm trying to show the various things from the span of S, I've got 1, 0, 0, 0 to work with. Because the obvious things that are in the span of S are V1, V2, V3, V4, V5. But in particular, that's also in the span of S, if I need it. Now, here's why that might be useful. Since this is in the span of S, and this is in the span of S, I can kill off the 1 here, right? Because I could just take this and subtract that. So that says that 0, 0, 2, 2 is in the span of S. And notice, I can kill this one off. I can kill the 1 here off here because this is in the span of S. Because if I add this to this, I get 0, 0, 1, -1 is in the span of S. Everyone? But notice, once these two things are in the span of S, if I take I can kill off the last piece, because if I take this one plus 2 copies of that one, I'm going to get 0, 0, 4, 0. In other words, this one plus 2 copies of that is this. But if I take this one and I subtract 2 copies of this, I can kill off this one, and that tells me 0, 0, 0, 4 is in the span of S. But if 0, 0, 4, 0 and 0, 0, 0, 4 in the span of S, that also means that so are 0, 0, 1, 0 and 0, 0, 0, 1. These are also in the span of S. Agreed? Which means, again, not only are these things in the span of S, but so are these 3. So the only one I'm missing is this one, right? And now, there might be something you might have observed 10 minutes ago. So if I'm looking at this, this, and this are all in the span of S. So the span of S is going to contain everything in the form, anything you want in the first slot, anything you want in the third slot, anything you want in the fourth slot. But what you might notice, and perhaps you notice this in the very beginning of the problem, everything here has a 0 in the second component, right? So any linear combination of V1, V2, V3, V4, and V5 is going to have a 0 in the second component. So I went through a lot of work because I took the approach of, well, what happens if I just sort of don't make any clever observations and I just sort of plow through brute force? So if I plow through brute force, this is in the span of S, this is in the span of S, this is in the span of S. The only thing that's missing is this, but what you might have noticed as soon as you start the problem is since I have a 0 in every position, any linear combination of V1, V2, V3, V4, and V5 is going to have a 0 here. Therefore, S cannot possibly span the whole thing. So in this case, S is not linearly independent. That was the easy part because it was too big. But S also doesn't span because if you take any possible linear combination of the 5 elements in S, you're always going to be stuck with a 0 there. So you don't get the whole vector space. So you might have just stared at this problem and immediately noticed that there's no way that you can get something other than 0 in the second spot. But if you had spotted that immediately, you wouldn't have asked the question, right? So that's why I took sort of a brute force approach of, I'd like to get all of these things into a spanning set. Rather, I'd like to get all of these things into the span, but I can only get 3 of them. So again, the point is, if you're showing something as a spanning set, there are an infinite number of elements of V that you need to check, technically speaking. But normally, you can usually just break it down to a finite number of things that have to be in the span, and then you can just look at them one by one. Questions? Anyone look at this problem and immediately focus on the fact that there was a 0 in the second component of everything? Oh. But I think what you can see is, if you multiply any of these things by a scalar, you still have a 0 here. And then if you add those things up, you still have a 0 here. So any linear combination is still going to have a 0 there. So in particular, that's not going to be in the span. So this is a set which is not spanning and not linearly independent.
The same, I mean, this might be a dumb question, but not linearly independent, does that mean linearly dependent?
Yes.
Okay.
Not linearly independent is the same phrase. It is the same as just the simpler phrase linearly independent. There was also a question on number 11.
I was gonna say, I'm fine with it now. When I was doing this, that's what I was doing, was getting the simple spanning set of 1, 0, 0, 0, etc. But it's time consuming and sometimes a bit of a, like, I don't know, like a crapshoot, trying to make it work. Like, I feel like you have to beat yourself over the head with it sometimes, and so I was wondering if there was a more straightforward or...
Well, for something like this, unless you made the quick observation that you always have a 0 in the second spot, that, you know, if there wasn't
so
something...
11 is the same thing then. If there's no quick observation, then you just have to hit it over the head with that.
Right. Now, I mean, in some sense, okay, I was looking at 12. Let's see if there's a quickie for 11.
Could you use matrices to do this?
Could you use matrices? If you know how to use matrices, how do you want to use matrices?
Well, there's a way to find the, you put in the matrices, but you have to put them in vertically instead of horizontally.
I mean, I mean, in some sense, what you're doing is you could reduce this to solving a system of linear equations.
Okay.
And then you can set it up with matrices and either have a calculator do it or use Kramer's rule, well,
Right.
presumably. Yes, there's a way to set this up with matrices.
Okay. All right. I just want to make sure that wasn't crazy. Well, I mean, solving systems, I've done that. Systems 3, 4, I can do that. But to figure this out and reduce them down, it's the REF button on the calculator, but I don't really, I have to figure out what it means.
Yeah,
So I can
errors. Yeah, I was trying that yesterday too, because I took a linear algebra course and it was all matrices based.
Right. So did I.
And so that's
Well,
trying to remember.
That's where the new 672 courses come in. That's when you play with the matrices, which would prep people for the 470 classes, which is the advanced linear algebra class. So if one were continuing on to the community college part, the matrix side of this thing would be in 672. At first time offered this coming summer actually.
I wouldn't mind that class. I know.
But yes, there's a way to do some matrices.
Well, there's only one class that's being offered for not the winter, that would be spring semester. Is there another class that we can take during that semester? So we don't have to take 2 in the summer. That would be, I know. I really don't want to do it in the summer. I really not in the summer.
Well, but that's not summer.
No, that's spring.
Right.
And that's the only class.
Unless, which I don't think it's likely, unless the differential equations course gets offered, the new 644 class. But I don't know if that's going to get offered this academic year. Well, in any case, to take the 644 class, you need the linear algebra. So
But if you had that as an undergraduate,
then we could waive the requirement.
if you had what as an undergraduate?
If you took linear algebra and you know of the stuff of basis and dimension, you also know how to play with matrices and so on. But we can talk about that in a minute. Okay. Oh, here's a question I should throw out to you as the consumers. We sort of stretched the quarter out to give you more time to prepare for the exams, like the regular quarter at DePaul actually already ended. Would you prefer things more compact, or do you actually want more time to study? Like, would you have preferred that this course have had its final before.
I'm gonna be miserable either way, I'm gonna be honest.
Okay. I mean, because I'm thinking since.
Then we wouldn't have gotten any weekends off ever.
Well, I'm thinking, I mean, DePaul is sort of uniquely quarter-ish, but for those of you who teach at schools, the quarter thing is probably sort of artificial, so being in school in early December is probably not a big deal.
I think the final Sunday is after high stuff.
Yeah. I don't like the Sunday. Because then you can study on Saturday.
Oh, yeah.
Like,
Instead of flying until Friday night, we work all day and then, yeah, I do like that.
Okay. So, for an overview, sort of your question, yes, sometimes you just got to get your hands dirty and calculate.
Okay, that's fine.
Look, I mean, in doing linear algebra, sometimes you just have to sit down with the basis and calculate.
How about one in the polynomial realm,
Okay.
like number 23?
Okay, so the polynomial realm is we're looking at the polynomials of degree less than 3. So the polynomials of degree less than 3, so P3 equals polys of degree less than 3. So the dimension of P3 is 3. So any set with more than 3 elements is guaranteed to not be independent. Any set with less than 3 elements is guaranteed to not span. And which set did you have in mind? Number 23?
Yep.
Okay, so what were the polynomials in there?
2x squared plus 1, 4x squared plus x plus 2, 3x, and 10x squared minus 21x plus 5.
Okay, so we're in a 3-dimensional space, and we've got 4 elements. So since the number of elements is more than the dimension, you can't be independent. Equivalently, you're dependent. Okay. Now, what about spanning? Well, unless there's something obvious, I don't know if there's something obvious, you might try to see if the simplest spanning set that you can think of is in the span of these things. And the simplest spanning set so the simplest spanning set you can probably think of is that the simplest spanning set you can probably think of? So the question is one in the span of these? Is x in the span of these? Is x squared in the span of these? So that's 3 questions. If the answer to those 3 questions are all yes, then voila, this is a spanning set. If the answer to any of those questions is no, it's not a spanning set. Jessica,
I have a question.
Okay.
And a headache, so don't take any of my facial expressions to be.
Okay.
Is another way to look at this. So in the past, we've talked about linear independence also as if I can write one of the elements as a linear combination of the other elements, then it's linearly dependent. Correct. Okay, so talking then about span, if I find that 2 of these 4 elements can be written as a linear combination of 2 other elements, not inclusive. So for example, the second element, I can get by doing 2 times the first plus a third of the second.
Okay. So here's the observation that you've made. And it's a good observation. The reason I call it a good observation is because that's the way that I would do it.
Okay.
So what we're doing is we're saying, I'm looking at the span of these four things, but there are redundancies here. I mean, I know automatically that it's dependent, but in particular, you can see a specific that I can get this one, I think this one, I can get this one by doubling this, plus, I guess, 1/3 of that.
Yes.
So anything that I can get using these three, I could have gotten just using these two, right?
Right.
So that means the span of these is the same as the span So the span of S is the same as the span of this, because basically what you showed was that's redundant. This doesn't add anything. Anything I can write as a linear combination of these four, I could have gotten as a linear combination of these three. So you've got it down to three things
And
now.
then I recognized that 5 times the first minus 7 times the second is now equal to the third.
Right. So what Jessica noticed is I can get the third one by taking 5 times this, that's 10x squared plus 5, and then some multiple of this takes care of the negative 21x.
Yeah.
So this is a linear combination of these two. So anything that's a linear combination of these three is a linear combination of these two. So frankly, if you're looking for a shortcut, I think you actually found the shortest way to do this, because that's
Because
sort of the way that
now
I would
we
do it.
know that there are fewer elements than the dimension, and therefore
Right.
it cannot span.
Right, so the span of S is the same as the span of these three, and the span of these three is the same as the span of these two. So S as a spanning set is the same as asking, is this a spanning set? But the answer is no, because it's too small. That's exactly what I was thinking when I did the problem. If you were going to do something like this by brute force, you could also discover that you can't write 1 as a linear combination of those 4 things. But yeah, I mean, what I would do is I would start looking for redundancies. So anything I can get in the span of these 4, I could have gotten without this one. And anything in the span of these 3, I could have gotten without that one. And once I'm down to just 2 things, it can't be a spanning set because it's too small. So in my mind, that's the easiest way to do this problem. If you didn't see it if you didn't make Jessica's observation, you could say, well, this is a spanning set if and only if each one of these 3 things is in the span. You might notice, obviously, X is in the span because it's 1/3 of that. But you can ask, is 1 equal to something times 2x squared plus 1 plus a constant times 4x squared plus x plus 2 plus a constant times 2x plus a constant times 10x squared minus 21x plus 5. Because what you might